In this video, I'm going to be talking about how to use calculus to find the volume of an object by introducing the slicing method. The slicing method is the basic method that the other methods that we will be using, such as the disc and the washer and cylindrical shells, are all built upon. So let's get started by doing something fairly geometric. So let's say we have a can, and I'll do an upright can. And let's just say that this can has a radius of 3 and it has a height of 10. And we want to find the volume of this can. Well, if we assume that it's a normal can and it has a constant radius, and that's very important, it has a constant radius, then we can just use geometry, all right? So basic geometric formula. And so what would that formula be? Well, the volume of the can would be the area of the top of the can, the cross-sectional area, which I will write A of x. The cross-sectional area is some function of x, times the height of that can. Well, because this is a circular can, we know the formula for the cross-sectional area. It is simply pi r squared, the area of a circle. So the volume would be pi r squared times h. And that's just the basic geometry formula that we know from, our educational past. And so plugging in the numbers, we have pi times 3 squared times 10. So the volume is equal to 90 pi. And so all we needed was geometry, but the key here is that the radius was constant. Radius is constant. And we know that calculus is the study of change. And so eventually what we're going to be doing is figuring out how to use calculus. What if the radius is changing? So to introduce the idea of slicing, let's take a look at this from another perspective. Let's take and lie the can along the x-axis. Here's the y-axis. And here is our x-axis. And let's take and make it look kind of like a can lying along the x-axis from here. It's going to start right at the origin. It's going to start right there. All right. As you can tell, my artistic skills are overwhelming. And now we want to find the volume of this again. So what we're going to do is we are going to slice this can into a bunch of tiny little slices. So let's just take one tiny little slice right in the middle of the can. Think of it as a loaf of bread, and you're cutting a loaf of bread. We're going to take one tiny little slice here. Of this can, just like we would take a slice of a loaf of bread. Well, the area of the slice, the area of one slice is simply going to be, again, the cross-sectional area of that slice. And because we know that the cross-sectional area is a circle, it would once again be pi r squared. Well, then what about the volume of that slice? The volume of one slice would simply be, just like we said in the previous example, it would be the cross-sectional area times the height. So once again, that would be pi r squared times h. But in this case, because this is along the x-axis, let's call the height of this delta x. All right, so this would be pi r squared delta x. Well, what if we want to find the volume of the entire thing? Then what we would have to do is we would have to take multiple slices. What about the volume of multiple slices? Well, the volume of multiple slices is simply going to be pi times r sub 1 delta x plus pi r sub 2 squared delta x dot up to pi r sub squared to n delta x. In other words, we're going to take the radius of all of these slices, divide them, multiply them by the thickness. Well, once again, remember that the radiuses are all the same, so we can simply write this as the volume is equal to the sum from I equals 1 to n being the number of slices that we have, of pi r sub I squared delta x. And so we add up all of these slices and we would get the volume. Now in calculus, we like to take things to extreme. What if we were to create an infinite number of slices? Well, then the volume, and by the way, this should be approximately here. So the volume would then be the limit as n approaches infinity of the sum from I equals 1 to n of pi r sub squared I delta x. And so that should look familiar. That is the limit of a Riemann sum. So this basically here was a Riemann sum, and this is the limit of a Riemann sum. And we know what we get from the limit of a Riemann sum. We get an integral. So from this, we can say that the volume is equal to the integral from a to b of pi r squared delta x. Or more generally, we could say that this was the integral from a to b of the cross-sectional area times delta x. And this is going to give us our basic formula for the slicing method. We are finding the integral from a to b of some cross-sectional area dx. So let's just see that this actually works using the same problem I used at the beginning of this problem. So we have a can where the radius is equal to 3 and the height was equal to 10. I would want to set up the volume is equal to the integral from 0 to 10 of pi times 3 squared dx. Well, that becomes the volume from 0 to 10 of 9 pi dx, which basically we would write 9 pi times 0 to 10 of dx. And then integrating that, we would have that the volume is equal to 9 pi x evaluated from 0 to 10, and that simply becomes 9 pi times 10 minus 0, which of course is 90 pi. So what we did was we just used calculus to find the volume of that can that we found at the beginning of this video using simple geometry formula. Now, this is the basis of the slicing method. This problem wasn't particularly difficult, but what will make it more difficult is when you have a radius that is constantly changing. And so in some of the homework problems that we're going to be getting into, we're going to take a look at how to do problems where the radius is constantly changing. As an example, what if you were asked to find the volume of a cone with a base of, let's just say 8 and height of 12. So that would be something like this. We have a base and we're going up to a cone. And so the height is 12 and the radius is, the base is 8, so the radius would be 4 because the entire base is 8. And so we can use this slicing method to find that. We will use the basic integral from a to b, volume is equal to a to b, of the cross-sectional area dx. And so that's what we're going to be talking about in class. And I might do another video on how to actually do this problem here very shortly. All right, so that's an introduction to the slicing method.